Well, hello, I'm here to talk about nanomaterials, and especially kind of soft type of nanomaterials. So I thought first to see, how small are we going? So I had this 5p coin, a 5 pence coin, and I do a little experiment with it just to see, how small can we go. So take this 5 pence coin, put it on the side like this, and then try to slice it in 18,900 separate slices. One of those slices will have a thickness of 100 nanometer. And that 100 nanometer is roughly the definition of a nanotype of material. So why is this important? Well, for example, the EU regulation this summer will say that in all cosmetic products, you have to basically mention the word nano. So if you go to a shop and you look into this formulation kind of thing, look at the backpack, then it will say, hey, there might be a nano product in there. So what can we do with this type of nanomaterials? And what does it actually mean that if we buy products, could this be good for us? Could this be bad for us? So I would like to take you to planet colloid, in a way. Colloidal matter are very, very tiny little particles that can be extremely useful, but also happen in the natural world. So for example, a latex tree, the tiny little milky substance that you tap off that tree consists of tiny little plastic balls that are made of polyisoprene, and that's a base for a rubber-like material. Man-made materials on the nanoscale are also already known, since the Egyptians, for example, they used to dye their hair and end up with lead selenide quantum dots in their hair fibers to blacken their hair a little bit more. So here on this picture, I've just shown you 4 types of materials of what we can make nowadays in the lab. So on the top left, you'll see tiny little cubes that are made out of glass, and they are hollow. And with those hollow materials, we can change optical type of properties. So for example, we can make paint look whiter. On the right-hand side at the top, you see a material that has got kind of squishy hairs in the middle and 2 kind of hydrophobic kind of blobs sticking out, and these things can self-assemble in all kinds of intricate structures. On the bottom left, you see it looks like a bit of ping pong balls, but these ping pong balls are 200 nanometer in diameter, and they crystallize in this beautiful larger, what is called a colloidal structure. These structures are used as structural colors. For example, the natural analog would be the color of a butterfly wing. And on the right-hand side at the bottom, you see actually a biological plant spore that is about 30 microns in diameter. The structure in itself already is very complex, but on top of the edges of this structure, we can add tiny particles to alter its properties so that it can either wet or not wet a surface it lands on. So I want you basically going through a bunch of experiments, really, and I've sketched them out what we're going to do. So here are 3 scenarios. In scenario number 1, we'll take a permeable plastic bag, in a way, made out of a very, very small block copolymer, and we're going to decorate it with even smaller particles on the outside. The reason why we want to do this is that this membrane is permeable, and we would like to control the release rates of matter that's enclosed in it. The second option is oil droplets in water. Everybody knows if you do the washing up at home, if you have one oil droplet and it bumps into another one, they fuse together. So how can we prevent oil droplets from fusing to each other? We can do that if we decorate it with small inorganic matter, with hard particles, in a way, that act like an armor, so that when these oil droplets now bump into each other, they bounce off each other rather than fusing into one. And the third little experiment would be, we take 3 different types of particles. One very soft and squishy, one that is conducting, so conducting carbon black, for example, and a tiny, tiny little silica glass bead. All those 3 together, we freeze into ice, and then we'll end up, hopefully, with a nice structure that can be used. So here are the results of our 3 experiments. On the top left, you see a beautiful structure of these hollow permeable membranes that basically can be used to deliver all types of substances at a very, very controlled rate. And at the bottom is this ice crystal type of material. This material that's made out of 3 tiny little particles can be used as an extremely sensitive gas sensor. And I would like to focus on the material on the top right. These are very, very soft polymeric particles that are wrapped around in tiny nanoscale clay. And these materials are extremely useful, for example, in scratch-resistant coatings and in flame retardancy. And for that, I will show you a little clip. In this particular case, you see basically that we'll light a polymer film up. And the really bad thing about this is, if plastic starts to burn, it drips. So, for example, if your house would be on fire, you do not want this, because it spreads the fire very, very quickly, and in about 2 minutes, your entire house will be burned down. If he would use this material now, which has this particular nano type of component in it, a same polymer film, for once, it burns a bit slower, and the second more important reason is that fire goes out quicker, but more importantly, it doesn't drip at all. So in this particular case, the fire will not be able to spread to surfaces that has not been set on fire yet. And as a result of that, you have a few minutes extra to escape a burning building. So let's take a little sidestep on this. We know now that we can wrap small particles with even smaller particles around that. So how, for example, can this be of use in food? Well, imagine that you put tiny little droplets of fruit juice in chocolate. Chocolate is nice and tasty, but chocolate can also be quite fattening. So if we can remove a bit of the fat and replace it with fruit juice, that could be a good thing. So in order to do that, we need to have these juice droplets not bumping into each other, and we learned already that we can do that with putting inorganic material around it. And for that we can use silica, which is allowed in food. Then secondly, you might know that water is more heavy than food, so if I have these droplets in molten chocolate, they will all fall down. For this not to happen, we kind of glue everything together with a type of sellotape of approach, and for that we use a molecule called chitosan. So that's like experiment number one. The other experiment what I want to show you is that if you think, for example, of noodles that are dried out, and you put them in water, they'll all spread out. If you want those noodles not to spread out, you might think of something like Velcro or paddleboard, and you can basically have every single chain with some of these things attached to it, and that glues everything nicely together. So those two concepts are extremely useful in making interesting materials. So let's look at the chocolate case first. So here you see a picture of, well, what we call in the UK, dark chocolate, milk chocolate, and white chocolate. And below that, you see that you have these tiny droplets of fruit juice that are less than 30 microns in diameter, perfectly dispersed in the chocolate matrix. The cool thing about that is, because they are so small, you will basically not sense that you'll have kind of these droplets present in the chocolate. You will taste it still a little bit. This material over here is a beautiful colored polymeric film that normally would disintegrate if you would expose it to a solvent. This material has got these Velcro, these pedal port bits in the molecular chains. And as a result of that, it stays intact when it's put into a solvent. So for that, you can make very, very thin solvent-resistant materials. Extremely useful. So now let's look at what we can do next. So we can play with particles, we can make really complex particles, but what if we can make these things really clever and make these things do things by themselves? So imagine if it would be possible that we have like some happy smiley particles that are sketched as the white ones, the spheres. They're in a fluidic river and they flow along quite happily. And then we have like these red ones that look a bit more cylindrical, and suddenly they realize there is food somewhere else, and decide to swim in an other direction by themselves, without us controlling it with an external joystick, for example. That would be really cool. That effect is called chemotaxis. The second thing would be, what if we could make a foamy wire that contains tiny little droplets? And what if this foamy wire could move by itself, if we trigger it, for example, by heating up the temperature, and could shrink and deform and release its content? And third, what if we would have like tiny little plastic bags that spontaneously could open up to release their content? Well, this is the edge of colloidal science, and these type of things start to become possible now. So here in this clip, if you focus on these really light little cylindrical bits, you can see they go to the dark spot on the top right, whereas the round spheres tend to move to the top left. This is like version 1.0 of clever particles that can do this type of chemotaxis behavior. Extremely exciting, because it basically means that you can have man-made small matter swim to a place where you want it to swim, and then do whatever you want it to do. In the next example, you see this wire. This is this foamy wire that by heating it up a little bit, it starts to wiggle about completely by itself, and it shrinks, and it releases its content. And last but not least, here you see a picture of these tiny little kind of plastic membranes. They're about 100 microns in diameter. And we can now trigger its content by itself. So in this particular case, you see that gas bubbles get produced at the surface, and its content is beautifully released. So to wrap up, I've shown you 3 things what is possible with colloid, nano-based squishy material. We can make flame-retardant coatings. We can alter your food to make it more healthy. And the next level will take us to a complete unexplored area of soft colloidal science. Thank you.